Number one. Now, copper exists in two isotopic forms. Copper 63 and copper 65. That's the way if you write it out longhand, you would do like this. Copper 63. So you may see it that way. But copper 63 and copper 65 are the two isotopes we're concerned with, and the atomic mass of copper is 63.5. So the 63.55 is atomic mass, and they're using atomic mass units. Okay, that's fine. What's the approximate natural abundance of copper 63? So we want to know this one equals such and such a percent out of those two isotopes, and we've got 65. Copper is the other one. Use a little algebra. Anybody remember algebra? The natural abundance. First of all, what would be the natural abundance? Well, if this one is, say, a fractional abundance value, then this one would be 1 minus x, right? Because we're only given two of them. So if this is a certain fraction, that's 1 minus the fraction. So why don't we let x equal the abundance of this one? And the abundance of that one is 1 minus x. So how do we calculate this right here? Well, we say this value, or for simplicity's sake, we're going to use these values. Actually use is the atomic mass of each of the isotopes. It wouldn't be exactly 63 or 65. Why? Because there's only one element, one isotope that has exactly a whole number, and that's carbon 12, because that's the standard. So in reality, these would be different numbers, but for argument's sake and to answer, we're just going to use these values. Okay. So what we would do would be we take a fraction contribution of this value, which would be 63 times x, and we would add to it the contribution of that value, 65 times 1 minus x. And that would be equal to this weighted average. Okay. So now what do we got? We got an equation in one unknown, and we can solve for it. Right. This would be 65 minus 65x equals 63.55, 63x, and combine our x values. So this 63x would minus 2x here, right? Plus 65 would equal to that value. And then we want to get all our numbers on one side and all our unknowns on the other side. So this would go over here, and this would be positive on this side, negative on that side. 63.55 minus 65 would give us a negative number, wouldn't it? What would be 1.45? Is that right? I think. And this would be equal to minus 2x. Let me make that clear. That's a negative one. Okay, so x would be equal to 1.5 divided by 2. And since they're both negative, they cancel. I mean, it's a positive number. Let's see. 1.45 and that by 2. 0.725. So x is 0.725. Well, we want it in percent, right? So percent would be, let's see, rounded. Well, these are exact numbers. So 72.5%. So the closest one to that out of that whole bunch is 70, right? So it's like I always say, if you values to deal with and you don't have any of those oddballs like 2 of the above and none of the above, that kind of garbage, then pick the best answer. The best answer that's closest to the value we got. If we used actual values I don't have on hand, then we get a slightly different number. All right, that was number 1. Let's see. Yeah, we can do number 3. I think I did that I did this one in the lecture part. The average mass of carbon atom is 12.011. That's because there's carbon 12 and carbon 13, maybe a few other minor ones. So we're not talking about just the carbon 12 isotope when we give that number. But assuming you were able to pick only 1 carbon unit, the chances that you would randomly get one with a mass of 12.011 is what? 0%. You would not find one with exactly that mass because it's a weighted average. It's not a real atom. It's an average of a collection of atoms. Trick question. Let's see. We want to tackle this. And what's the mass of 4 atoms of copper in grams? Okay. Analysis time. If we've got 4 atoms of copper, 4 atoms, now we're going to go from that to mass, to grams. Right? Now we're going to get there. Right? We don't have any direct conversion from atoms to grams. What do we have? Pockets ticking. We have molar mass. That converts from numbers of atoms to atoms. So we got to get this into some form that we can use molar mass. In order to do that, we can convert atoms to moles, right? So how many atoms? Remember that one? 6.022 times 10 to the 23rd. So that gets rid of atoms and leaves us with moles. Now what we need is molar mass for copper. Right? Copper. So we go over here and look. 3.55 rounded off to 2 places. Right. That gets rid of moles. Now we, and if I do my math right, it should be in time. I'm not going to whip out my calculator. It should be that much for 4 atoms. 4 atoms of copper. Okay, kind of small. That's what we would expect. Have a really small value for just 4 atoms. We got any, yeah, we got some strange ones in here, like 154 grams for 4 atoms. That would be heavy metal. That's pretty big too, and that's pretty big. So you can basically throw that one out, throw that one out, throw that one out, and be one of these. Logically speaking. All right, let's see. Do I want to stop on this one? Yeah, okay. This uses a little logic. If we have a sample of zinc and a sample of aluminum, and you have an equal number of atoms, right? So the moles of zinc equals the moles of aluminum. Exactly the same number of atoms. Which of the following statements concerning the masses is true? Well, let's say, what would the masses be? Right. Say, it's okay, we can say 1 mole of this is 1 mole of that, right? if we're just doing a comparison. So a mole of zinc is 65.38 grams for 1 mole. And 1 mole of aluminum is like 26.98 grams. Okay. So if we have equal number of moles, aluminum is going to weigh less than zinc. So let's see, we got one in here that works. Zinc sample is more than twice as great as the mass of the aluminum. Well, let's see, what's twice that? It's almost 27, so it'd be what? 54? Yeah, it's more than twice. That's true. The masses are not equal. The mass of aluminum is not more. Mass of aluminum is not more. Mass is more than the mass of aluminum, but it's not twice. Okay, B can't be right. C, D, and E, we cancel those out easy. So compare A and B. Yeah, it is twice, more than twice as much. So A has to be the answer. Let me see. I don't know if I can do this remotely. If I can. Oops, too far. That's what I have. We're over here, right? I'm gonna skip 7 because we've done a conversion for molecules. And do 7. The reason I want to do 7 is because I don't remember if I told you what ammonia was, and you need to know the formula in order to do this calculation. So ammonia is NH3. And if you get a problem like this with a molecule we haven't discussed and there's no way you can figure it out, just ask me. That's ammonia. And we have 43.5 grams of it. Okay. How many molecules are in the sample? Well, I think we're going to have to, in order to work our way to molecules, we need molar mass. Okay. Yeah, I think so. So how do we get molar mass for ammonia? How much does nitrogen weigh per mole? Can you see it from over there? 14. Okay, we'll round it off to 2 places. 14.01 for nitrogen. And then each hydrogen 1.01. So altogether is 3.03, right? We can do that one on our heads. 17.04. So we can convert this grams. Let's put it down here. And the first thing we want to do is get rid of the grams and leave us with moles. Now we went from mass to numbers. So this is 17.04. Cancels grams. Now we can go from moles to numbers of molecules, because we're still talking about the whole molecule. So how many molecules in a mole? Same as before. Molecules. Moles. That's it. That's the thinking part. The rest is number crunching. So 43.5 divided by 17.04 times 6.022 times 10 to the 23rd should give us 1.54 times 10 to the 24th molecules. Let's see, is that reasonable? 17, and that's about less than 3. Times that. Yeah, okay, I'll go with that. Just doing a quick estimate. I didn't put the number of that one up there, did I? All right, for number 8, in order to solve number 8, look, it's a word problem. moles of hydrogen sulfide are contained in the 49.7 gram sample of gas. Once you know what the hydrogen sulfide formula is, you can go from there. That's the trick to this one. You got to know what hydrogen sulfide is, how it's written. As we see, sulfur is in the oxygen group, so it's -2. Oxygen, when it's first in the +1, so you need 2 of them. H2S is hydrogen sulfide. Now from here, you can calculate the molar mass and find out how many moles is 49.7 grams. Right? We don't need to do that one, do we? It's in the work problems anyway. All right, for which compound does 0.256 mole weigh 12.8 grams? For this one, number 10, we need Henry Ford. Or none of these. So if we have this one, and this one, and this one, and this one. So we're going to need to convert 0.256 moles into grams. Like each one of them. Same thing all the way down. So what do we need? If we're going to convert it into grams, we need moles on the bottom, grams on the top, right? That means we need molar mass for each one. Okay, what's the molar mass of this one? Well, let's see. What's 1 carbon? Rounded off to 2, 12.01. Right? We got that one on the previous problem. All right, and then 4 hydrogens is 4.04. And then 1 oxygen, rounded off, 16. 16.00. So this is 4406. Right. I've already got it in my calculator, so I'm going to go ahead and do that. So the moles cancel, and we left with grams, 0.256. This is 11.28. Well, actually, it ought to be 11.3. Rounded off. Correct significant figures. I'm sorry. That's not it. That's not the one. How about carbon dioxide? So that's 12.01 for carbon and 2 oxygens. 32. 4401. Okay, times 6 is 11.3. That's not it either. But this one, 12.01 for carbon, 3.03 for the hydrogens, and what's chlorine? And I see you back there.
Yeah, I can't see that.
35.45.
35.
Yeah. So that's 50.49.
Times 0.25.
Yeah, 0.256 is 12.9.
Close, not it. Or is that it?
Ooh, yeah, technically.
Could be it, huh?
Technically, you could argue if the other two are not,
Right.
you could argue that it's E. Because it's not exactly 12.9. Did I do that calculation correctly? 50.49 and 0.256. Yeah, 12.9. Okay. So you could argue your case that if you answered E, you were right. Assuming these two are not. So let's check. Let's see, 12.01 times 2 and then plus 6.06. If I did that right at 3008.
That's not exactly it either, then.
No. It would have to be really close to this to be even have a chance with it.
So that'd be C or E, huh?
Yeah, so you could say this or that. So if you have that option, I think you'd be correct with either one. And if you put E and I mark it wrong, you can argue your case. So, show me your work, this is it, okay. That's credit. You know, make like a Boy Scout, be prepared. Argue your point. Okay. Here's one, 11, where you have to be able to write the compound, otherwise you're stuck. So barium sulfite is what? Well, barium, right? What's sulfite?
S. To the.
How many O's? Does it have oxygen in it? Yeah. How many of them?
2.
That's sulfur dioxide. Try 3. Okay, that's atomic, right? And you will have access to the list of polyatomics. But it's the brain every now and then. This has a charge of 2 minuses. Barium is from the second column, alkaline earths. So it always has a 2+. Right. 1 and 1 is all you need. And then we just add up the barium, which is 137.33. And sulfur is 3207. And 3 oxygens is 48. Yes. That's 10, 4, 17, 6, 8, 11, 217.40. There. Grams per mole. Right.
Looks so easy.
Uh,
Make it all look so easy, and then just when I look at it without you, my mind just says blank. But whenever you just started, it was all confessed.
you practice them.
Yeah.
Work all these problems. Have you worked through these at least once?
You're good.
Okay. Okay. What's the mass of 6.761 sample of sodium hydroxide? This is a unit conversion after you know that sodium hydroxide is that. Because oxide is a polyatomic ion.
12 or 13.
13? Did I skip one?
Yeah. Thought we
Oh, no, we're not, 12's not
were not
marked.
even 12, gotcha, okay.
So once you know that, you can add up sodium, oxygen, hydrogen, find your molar mass and convert it to grams. Okay. Let's see, that was chopped off over there. Roll it. One molecule of a compound. This looks interesting. Weighs 3 times 10 to the minus 22 grams. The molar mass of this compound is. Okay, this is another unit conversion. You start with 2.93 times 10 to the minus 22 grams. And this is 1 molecule per molecule. Right? So we per mole. All we have to do is convert molecules to moles. So this times that would give you your answer. Cancels molecules, grams per mole. And that should be equal to 176. Oh, this is interesting. Let's do this one. A compound is composed of element X and it's got X in it, it's got hydrogen in it. We don't know how much though. Right? So this would be some subscript. The line would be, right, we don't know that yet. Analysis shows the compound to be 80% X by mass. 80% X. Mass. Okay. With 3 times as many hydrogen atoms as X. So 3 times as many hydrogen atoms means that B is equal to 3 times A. This value here is 3 times whatever A is. Which element is element X? Okay, so what do we need to know to determine what X is? Well, there are 2 ways you can identify an element. One is the atomic number, if you have access to proteins. If you don't, then your next best thing is atomic weight, or atomic mass, because they get bigger from top to bottom, left to right also. And sometimes you can nail it that way. And I think that's where we're going to this one. So we need to know the atomic mass of X. Well, 80% of X by mass of this compound, and 20% is hydrogen by mass. I can't do anything with this one because we don't know what X is. But if 20% of it is hydrogen, then why don't we assume, since these are relative to each other, per 100 by mass, we could say so many grams per 100 grams would be parts per 100. So if the whole sample were 100 grams, if we assume 100 gram sample, then we have something we can work with. Now we know we've got 20 grams of hydrogen. So how many moles is that? Well, we need 1.01 gram per mole. 20 divided by 1.01 is 19.8. So that's 19.8 moles if it's grams. And then the ratio is B is actually 3 times A. So what would A be? A would be equal to B divided by 3, wouldn't it? Right, so if we want to find out how many moles this is, if that's 19.8 moles, then divide by 3, and that's the moles of X. 6.6. So 6.6 moles of X. So we got the moles. What do you need to know for molar mass? You need to know mass and moles. So we got the moles. Can we get mass out of it? Well, if this is 20 grams, that means this is 80 grams. 80 grams per 6.6 moles. Okay. Oops, I did something wrong. Let me try. 6.6 divided into it. There we go. Round it off to 2 places. About 12 grams per mole. Did I lose anybody? Does anybody want to admit that I lost it? So my focus at the beginning was find the molar mass, grams per mole. 12 grams per mole says it's carbon. carbon. And the formula doesn't ask us the formula, but if we wanted to, we could do the empirical formula would be carbon. Like that. There's just one problem with that that you probably wouldn't recognize is there's no such thing. It doesn't do that. If carbon's got any hydrogen with it like this, it's CH4. So probably we should modify that problem to be more closer to reality. But we answered the question. As far as exams go, that's all that matters, right? Satisfy the gatekeeper and you're on your own and you're on your way. 18. Let's see, how am I doing on time? Gotta finish up. 1:45. So done with chapter 3, so I can get into chapter 4. Which one has the highest percentage of mass by mass of hydrogen? In order to do this, you would use that method to convert. Yeah, go forward again. And we'll just do one of them. If you're going to do HCl and find out percent by mass of hydrogen.
Say one, scoring was what, 35%?
1.01 on top and 1.01 on the bottom, because this is the total and this is the amount of hydrogen, right? 35, 45, and times 100, and whatever that value is. Do that for each one of them. If you have 2 hydrogens, you better put a 2 up there. You better put a 2 down here.
Oh, and that's the highest percent, that's why you did times 100.
Highest percentage. Yeah.
Right, that's why you did times 100. I was wondering why you
Yeah.
did times 100. Okay, I got you.
Yeah, we really don't have to. I mean, to do a comparison, but that's okay. If you have 1 hydrogen, you can use 101, 101. If you have 2 hydrogens, it's 2.02 and 2.02. All right, and then just follow in Ford's footsteps and compare, and you should come out with water as the highest percentage of hydrogen. Now, does that make any sense?
Yeah.
Yeah. When you compare the others, right? This is massively huge for hydrogen. This one's got 2 hydrogen. That's a pretty good candidate. This one's got sulfur stuck in there, so hydrogen is going to be a pittance. This one, 2 hydrogens and 1 sulfur, but oxygen weighs less than sulfur, even though they're in the same family. That's oxygen and sulfur. So sulfur's percentage of this one than it is that, than oxygen is of this one. So that one wins out if you compare these 2. And then hydrogen and fluorine. Fluorine's about 19, I think. Yeah, fluorine's 19. Oxygen's only 16 with 2 more hydrogens. So that wins the battle there. And it, actually, you should be able to reason it out if you want to go that route. If you'd rather calculate it, that works too. 19. Let me see. We need to do this one. Substance contains 35 grams of nitrogen, 5.05 hydrogen, 60 grams of oxygen. How many grams of hydrogen are there in a 153 gram sample? All right, for this one, we're actually using Lavoisier's law. Conservation of mass. No, we're not. Not conservation of mass. This is definite proportions. That's Proust's law. Says that once you establish the ratio by mass of every element in the compound, it doesn't matter how much compound you have, it's always the same ratio. So you just find out what's the ratio of, let's see, what are we looking for? The ratio of hydrogen to the total. So this one would be divided by the total mass of all of them. And you can just use the fraction actually. And then multiply the fraction times. Oops. You would do, I'll set it up for you. So you'd have 5.05 grams of hydrogen, and then the total mass would be 5.05 plus 35 plus 60. That would be the fraction. You wouldn't even have to do a percentage. That would be the fraction of hydrogen in the total. So the fraction in this total would also be the same fraction in 153 grams. So you just multiply that times 153 grams. And it should come out to 7.72 grams of hydrogen. Okay. Each molecule of testosterone contains 19 atoms of carbon. The mass percent of carbon in testosterone is this. What's the molar mass of testosterone? This is unit conversion again. Yeah, maybe we better do it. 19 atoms of carbon plus the other atoms. The mass percent of carbon in testosterone is 79.12%. So it's got 19 atoms of carbon, 19 plus something else in testosterone. We're not told what the molar mass of testosterone is, but we are told the percentage of carbon. So the percent of carbon in this molecule is 79.12%. So that means that the fractional equivalent would be 0.7912 would be equal to the mass of carbon divided by total mass. Okay, and this would be actually the mass of the others plus the mass of carbon. All right, if we're going to define what's the molar mass of testosterone, this is 19 atoms of carbon per molecule. I think that's a better place to start. I was just thinking out loud here. If we're going to get molar mass, we're headed toward grams per mole. Of testosterone. So if we've got 19 atoms, what mass is that? Well, carbon is 12.01 grams per mole. And if we have 19 atoms of carbon, we need to convert that to moles. Right, so that's 6.022 down to 10 to the 23rd. So that gets rid of moles, gets rid of atoms, and that leaves us with grams of carbon in that molecule, doesn't it? 19 atoms to moles to grams. So this is the number of grams in the molecule. Let's do that calculation. And divided by 6.022. Third. So that's 3.789 times 10 to the minus 22 grams of carbon in. Okay. Now, what's the mass of the molecule? Right? What's the mass of the molecule? Well, it's 0.12% carbon. So this right here represents 79.12% of the total. So if this is 0.7912 of the total, and divide that into that, and you got 4.789 times 10 to the minus 2, 22 grams per molecule. Okay, now we've got something we can work with. All right, how many molecules in a mole? We want to cancel molecules. Right, that would be grams per mole for the compound. So this is another. I get the feeling there was a quicker, easier way to do this.
Yeah, I would say on your paper, you did it way easier.
Okay, let me see if I get the same answer.
Okay.
6.022 exponent 23. So I get 288 grams per mole.
You're close to a decimal.
Yeah,
Or one.
okay. Oh, yeah, 0.4.
Yeah, it should be.
Yeah, I just didn't put the 0.4 up there. Okay. Yeah, when I'm trying to think on my feet, sometimes I dance around the barn 2 or 3 times.
19 atoms of carbon over molecules, and then 12.01 molecules over atoms. And we got 228.19 AU over molecules.
Okay.
Yeah. And then you went down and done.
Okay.
Yeah. So you should have-
I did it 2 steps there instead of 6 steps here.
Yeah.
So
So I was on the paper, and I was almost getting the paper, and I was looking at the board, and like, you completely lost me there.
the moral of that story is I shouldn't take my own exams because I'll be half an hour trying to solve one problem. An oxide of iron has a formula Fe4. What mass percent of iron does it contain? I don't think we need to stop there. You can do that one, like 3 molar mass of iron divided by the total, which is 3 times the molar mass of iron plus 4 times the molar mass of oxygen times 100. So I think you manage that one. Ammonium chromate contains what percent nitrogen by mass? The important part of this one, 26, is to recognize that when you have 2 ammoniums in the formula, you have 2 nitrogens. So when you calculate the percent nitrogen, you need to take that into account. Nitrogens in both the numerator and the denominator, 8 hydrogens, 1 chromium, and 4 oxygens. That's the important lesson here. Okay, an empirical mass problem. This one should be pretty quick because it's only got 2 elements in it. Carbon and hydrogen only. That's why we call them hydrocarbons, hydrogen and carbon. That's it. 85.6% carbon. 85.6% carbon. So how much hydrogen is it? 144, I think.
Yeah.
Okay. So to find the empirical formula, we're stuck there unless we make an assumption. The sample size is 100 grams. Assume 100 grams. Now we can call this 85.6 grams. We've got something to work with. And we can convert these to moles because the formula of a compound is numbers of atoms ratio, not mass. So it has to be converted to moles, some value of numbers. Hydrogen is 1.01 here, and carbon is 12.01. So if we do 85.6 and divide that by 12.01, 7.13 moles. And 14.4 by 1.01 is 14.3. Okay. Normally what I would do is reduce these to as close to whole numbers as possible and then start with the lowest one. Divide this one 7.13. Divide this one by 7. Yeah. And this one is approximately 2, and this one is exactly 1. So the ratio is 1 carbon and 2 hydrogens. And that's the empirical formula, the simplest whole number ratio. If we were going to the molecular formula, what would I need? I need the molar mass determined by some independent method. I'd have to know the molar mass of that compound in order to make the jump from here to molecular formula. But we're not given that data, so I'm stuck. Well, not really, because that's not the question. The empirical formula of styrene is CH. Okay, so they've already gone through the empirical formula part. Now we're going to get to, for this problem, we're going to get at the molecular formula. So if styrene empirical formula is CH, then the molecular formula is going to be some multiplier times that, because this is the simplest whole number ratio. The ratio will not change for the molecular. We just need to find out what the multiplier is. And the way you do that is say, what's the empirical mass for that? It's 12.01 plus 1.01. 32 grams per mole of that formula. And we're given 104.1 is the actual mass. Right? So if you look at it this way, we're going to take CH, whatever the molar mass, the molecular formula is, and divide it by this one to find out what that ratio is. Right, so I'm going to do this one divided by this one, and that equals what? 7, 8, 9. 9's too much, isn't it? 8. It's about 8, isn't it? Yeah. So X is 8. Now C8, H8. Adipic acid contains carbon, oxygen, hydrogen. What's the empirical formula? That will eat up too much time to do that one. But you do it the same way we did for the earlier carbohydrate. You just put the percentages down here: carbon, hydrogen, oxygen. Assume 100 grams. Now you've got grams to work with, converting to moles, and then smallest one, divide everything through by the smallest one. That'll make one of them 1, and the rest of them will usually be a fraction. Like could be something 0.5 or something 0.33, where a whole number multiple will convert everything into whole numbers. And besides, it's worked out in the handwritten problem set anyway. I want to get to something we haven't done before. Vitamin C, This one goes through all the way from empirical formula to molecular formula because we have molar mass right here. So I'm gonna skip that one too. 36. Okay, this won't take you just a minute. How many of the following are true concerning balanced chemical equations? Roman numeral 1, the number of molecules is conserved. Nope. Let's see. 1, 2, 3, 4, and 5. That one's wrong. You don't conserve the number of molecules, you conserve the number of atoms of each element, respectively, on each side. Coefficients of the reactants tell you how much of each reactant you are given. That's kind of misleading because it doesn't say what they mean by how much. Usually what how much means is mass. So that's not right. It's not, you don't, the balanced equation and the coefficients don't tell you mass relationships. They tell you mole relationships, numbers. Atoms are neither created nor destroyed. Okay. Right. That's true for any equation, whether it's balanced or not. No, I guess it is. It has to be balanced. Sorry, it does have to be balanced in order to satisfy 3. The coefficients indicate the mass ratios. No, that's another way of saying 2, and it's wrong. And 5, the sum of the coefficients on the reactant side equals the sum on the product side. Nope, not necessarily. Because the coefficient in front of a compound has a different effect on each one of the elements. So the only one that's true is 3. There's only one that's true out of that, all those statements. Okay. In balancing an equation, we change blank to make the number of atoms on each side of the equation balanced. We change the coefficients. Okay. Once you've got the compounds and the elements written correctly on the reactant side and the product side, then you can't touch their subscripts anymore. Right. They're inviolable. The only way you can balance the equation once you've written the compounds correctly is with coefficients. So that's this coefficients of the compounds. All right. All right, we'll balance this one. We'll do at least one balancing. I don't want to have to come back after lab again. I'm trying to get through this before. So what's the coefficient of oxygen in this one? All right, so we have the beginning equation here. I'm going to leave the states out just to conserve room because they won't be necessary for this. Water. All right. So if we use the budget method, take nitrogen, hydrogen, and oxygen. That's everybody. On this side, we've got 1 nitrogen, 3 hydrogens, 2 oxygens. Right. 2 oxygens. 3 nitrogen, 1 nitrogen. Okay, 1 nitrogen over here, 2 hydrogens, and 3 oxygens. Okay. Should we use one of the hints? Yep. Don't touch oxygen coefficient until last, because it's a single element. And let's see, nitrogens are already balanced. We'll leave those alone for now. Hydrogens, we could do the hydrogens, or we could do the oxygens. No, let's do the hydrogens. I think that would be better. So we got 3 on this side, but we got 2 on that side. So remember that other hint. If you have an element in one place on one side and one place on the other side, and you've got an odd and even, cross multiply. So if we say 3 on this one and 2 on that one, that will give us 6 hydrogens here and 6 hydrogens there. But it also changes the nitrogens here. And it changes the oxygens from 3, 4, 5 over here. Okay. Now we need to balance the nitrogens. So we need 2 on this side. 2 nitrogens, 4 and 3 is 7. 7 oxygens. Okay, so we've got nitrogens and hydrogens balanced, but the oxygens are not balanced. So we've got a 7 here that we need 7 oxygens on this side. So there's another trick. Remember that one? Use a fractional coefficient. A fractional coefficient, 7 halves, will give you 7 oxygen atoms. Okay. Because a half of O2 is an O. And then 1 times 7 is 7. Now, we got to finish off by getting rid of that fraction. So we multiply the whole thing through by 2. So it makes this one 4, makes this one 7, and that should be our answer. It makes this one 4 and makes this one 6. So to answer the question, what's the coefficient of oxygen is 7. Okay. So we use 3 tricks in that whole thing. All right, if we have any more balancing, we'll have to skip them. Some of the coefficients. The moral of this story is for 40 and for any others, if it asks you for the sum of the coefficients, don't forget the number 1. If you've got a compound in there, there's no explicit number in front of it, it's a 1. So be sure and add that 1 in. Because if a multiple choice question is set up properly, it will take into account the most common mistakes that students make. And it'll put that answer in there also. So you may see the answer you got, but it could be the wrong one. And so maybe it was, you put 7, but you forgot to add 1. It should have been 8, just for example. So just a word of caution. When you finally balance the equation and you add the coefficients, be sure you get all of them. There's another sum of coefficients. We're not going to mess with that one. I will say this though. So, get that out of the way. That whenever you have a hydrocarbon and a combustion, where you burn it in oxygen and make carbon dioxide and water, you're always going to have to use that fraction trick at the end. Fractional oxygen. Okay. The only one that doesn't do that is methane. But the rest of them, all of them, above 1 carbon, will always have a fractional coefficient for oxygen as an intermediate step. Let's see. Number 44 is a word problem that requires that you be able to, you'll be able to write the compounds in order to balance the equation. So we'll go that far. Right? It says that sodium carbonate reacts with hydrochloric acid to produce sodium chloride, carbon dioxide, and water. Right? So that one's right, that one's right, that one's right, that one's right, that one's wrong. Carbonate has a 2- charge, so we need 2 sodiums. Okay. Remember that. You will see it again this afternoon in your experiment. So once you've written them correctly, then you can go balance them. Okay. 45. Chemical reaction has an equation 2A plus B, you'll see. So you need to find the right ratio of A and B. Stoichiometric ratio on A and B. You need two A's for every B, yielding us, well, stoichiometric ratio of A and B. Right. So what I read this as is this is before the reaction occurs. What's the stoichiometric ratio before the reaction occurs? That means you won't have any C in there. So let's see. 1, 2, 3, 4, 5, 6, 7, 8 A's and 1, 2, 3, 4 B's. That works. How about this one? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Nope, that's 1 to 1. And 1, 2, 3, 4 A's and 3, 4, 8 B's. It's switched around. This one has 1, 2, 3, 4, 5, 6, 7, 8 B's. Well, you don't even have to worry about the C's because the A-B ratio is wrong anyway. So A is the only one that has it. 46. A 7.11 gram sample of potassium chlorate was decomposed according to the following equation. How many moles of oxygen are formed? Okay. Looks like we'll be coming back. 46. This is a stoichiometry problem. Fortunately, they went ahead and balanced the equation for you. You're starting off with 7.11 grams of this. Right? And the question is, how many moles of oxygen? So what you need to do, remember, in a balanced equation, you can't go anywhere unless you moles. If you're grams or if you're milliliters of a solution, doesn't matter. It's got to be moles before you can move. So we convert this into moles with the molar mass of potassium chlorate. So potassium is 39.10. And chlorine is 35.45. And 3 oxygens is 48, right? I remember. 122.55. Divide that into 7.11. And you get 0.0580 moles. Okay, that's moles of potassium chlorate. How about moles of oxygen? Well, we need a conversion factor. And the conversion factor is found in the coefficients of the balanced equation. Right? You want to get rid of KClO3 and leave yourself with oxygen. So the ratio is 2 to 3. So I divide 2 into that value and then multiply it by 3. And I get 0.0870 moles of oxygen. D. Okay. Now the question has been how many grams of oxygen? Take that moles and convert it back to oxygen grams using the molar mass of oxygen. Let's see, I'm going to have to scroll a little bit and see if this one's worth stopping with. Now this is an excess problem. How many grams of calcium nitrate can be produced by reacting nitric acid with 6.33 excess nitric acid with 6.33 grams of calcium hydroxide? You need the balanced equation. Yeah, maybe better at least show you the balanced equation. What you got to do is fill in all the reactants and products. So we have calcium nitrate reacts with nitric acid. And we know one of the products is calcium hydroxide. But what else does it produce? Wait a minute. Acting with, oh, sorry. That read my own problem. We're reacting calcium. Probably a spoof. Okay, now we're going to produce calcium nitrate. Plus what? Did we talk about that? When you react an acid with a base, what do you get? You get a salt, the calcium plus the nitrate, and what's left over? Hydrogen and hydroxyls together makes water. Okay. So if we've got two OHs here, we need two hydrogens to make two waters. And that gives us two nitrates there and one calcium. That's balanced. And you can do it with budgeting. That works too. And nitrate is the same on both sides, so you can use it as a budgeting unit. But the hydroxyls have to come out separate and react with this hydrogen. So now we have 6.33 grams of calcium hydroxide and excess acid. And the question is, how many grams of this do you produce? So since this is excess, all you have to do is convert this to moles of that product. Use the 1 to 1, right? It's the same number of moles. And then convert the moles of this into grams using its molar mass. Okay. All right. Let's see. I'll skip that one. 58. Silver nitrate react with barium chloride. According to this equation, 3.17 grams of silver chloride. What's the percent yield of silver chloride? All right, for 58. The question is, what's the percent yield? So if you react this much silver nitrate with, I assume, excess barium chloride, then you're going to produce stoichiometrically a certain amount of silver chloride. Silver nitrate, this amount produces so much silver chloride, and you find out the mass of that that's produced from this. That's 100% efficiency. But we actually are given this value for silver chloride recovery, which is probably less than the value that you get. So what you want is to get percent yield. You want to work that equation stoichiometrically to find out the theoretical mass. And then you're given the actual mass. Then you can calculate the percent yield. Okay. Let's see. The next one was this one. All right, this is a limiting reactant problem. 59. How do I know it's limiting reactant? Because we're given exact amounts of methane and exact amounts of chlorine, exact amounts of this reactant and that reactant. When a problem does that, you can assume that one of them is going to run out. So you got to figure out which one runs out first. That's the limiting reactant. And that will limit the amount of carbon tetrachloride that's formed. So we're given the balanced equation. Maybe I'll do this one. 4 chlorines. It was carbon tetrachloride plus 4 HCl. All right, so we're given 1.2 moles of methane and 1.11 mole of chlorine. And we want to know the mass. Okay. Normally what you would do is say, convert this to the number of moles of carbon tetrachloride, which is actually equal. So if this one is reacted, it would give you, all of this would give you 1.20 moles of that. That's from this one. If this one were reacted, the ratio is 4 to 1. So we would say 1 moles of chlorine and convert it to carbon tetrachloride, which would be 1 here and 4 there. Correct? Ratio cancels this one. So 4 into that one would be less than 0.3. It's like about 0.28 or 29. So we can tell from that without having actually, well, actually we would have to do it. I'm sorry. We would have to do that because we got to convert it into that. So 4 into 1.11 is 2775. I'm going to keep all my decimal places for now. And then we convert that into mass using the molar mass of carbon tetrachloride. So we got 12.01 for carbon and 4 times 35.45. Let's see. Yep. Checking this out. 153.81 is the molar mass of carbon tetrachloride. So we multiply these two values together, and that'll give us the mass. And they're both in my calculator. All I have to do is hit that button. And I've got 3 significant figures I can keep. 42.7 grams. Right there. Okay. That was a limiting reactant problem. And we would have some leftover methane in that reaction. All right, I'm out of time. I'm gonna have to come back and pick that up. You know, I want to leave this thing running. Yesterday, I paused it and forgot to unpause it, did the whole lecture without recording it. So I think I'm going to let it run and just chop it out later. We can do that with pro accounts. Yeah, unlimited storage. With the free accounts, nope. Free accounts, they cut you off for 45 minutes within, or 50 minutes. Okay, which of the following statements is always true concerning reactions represented by the following balanced chemical equation? All right. So, here's my pointer. Which one of these statements is always true concerning this reaction? All right. Notice the answers. Masses, limiting reactants, and numbers of molecules. We already have access to the numbers of molecules because we have the coefficients for the balanced equation, but we don't have masses yet. So what would the mass ratio be for these? Let's see, 2. I think I need a new marker. These things don't last very long. 2C2H6 plus 7O2, 6 water. This one's crapping out on me too. All right. This one. So we know the number ratios or the mole ratios are 2, 7, 6, and 4. Mass ratios would be the molar mass of this times 2. That's how you get the mass ratios for this reaction. If you were doing a stoichiometric ratio,
32 times 2.
I'm sorry.
So C2 times 2.
Oh, yeah, we have to get this molar mass first. Right, so it's 32 and then 6.06 for hydrogen. Okay, so this will be 38 times 2 would be 76 grams per mole. All right, so that's for the ethane. Oxygen would be 7 times 32. 224 grams per mole. And this one's bombing on me too. Going to my private stash. Water is 18.02 for each one of these. Times 6. .108 grams per mole. And carbon dioxide is 12.01 plus 32. 4401 times 4. So it's 176.04 grams per mole. All right. So these are the stoichiometric mass ratios. 76 grams of ethane plus 224 grams of oxygen yields 108 grams of water and 176 grams of CO2. Now let's see if that's right. If we did that right, then total this should equal total of that, right? Conservation of mass. So I've got those last two in here. Let me add those together. Okay. And then 224 and 76 is not exactly right. What did I do wrong? Should be the same. That's 12.01 times 2 and 6.06 plus 30.08 times 2. .16 and then 224 plus, and then add those together 108.12 76.4. Yeah, that's right. Add these two together, it's exactly equal to these two. So the mass ratios are these values. Okay, now we should be able to answer these questions. Which ones are always true? If we have equal masses of C2, H6, and O2, there's no limiting reactant. Equal masses? Well, say we have that's equal to that. This has excess, and that would be limiting. Right? So equal masses means no, equal masses means there is a limiting reactant. Right? Equal masses, whether you do it, make them both equal to this one or both equal to that one, still this one would be limiting if they were equal masses. Right? So A is false. How about B? If we have an equal number of moles of C2H6 and O2, there's no limiting reactant. Well, that's obvious. It takes 7 of these for every 2 of those. So if they're equal moles, say if you got 7 here and 7 there, that means this is excess and that's limiting again. So B is false. How about C? if we have more mass of C2H6, then, that should be than, not then. No, I guess it is. If we have more mass of C2H6, then O2 must be limiting.
That's true, right?
If we have more mass of this than that, yes, C is true. That's true. None of these statements are true is E, so that's it. We're done. E is not true, and we found the right one, and there's no two of the above. So once you find the right answer, you can stop. Okay, that was 61. Why I forget. Make a note. That's this lab is moved. Let's see, this one's gonna move. This date up here. Yeah. Technically, that means that the lab that we do today is now due next week. If you haven't done it yet. If you have it, that's fine. Yeah. Let's see. 62. Equal masses in grams of hydrogen gas and oxygen gas are reacted to form water. Which substance is limiting? For this one, you've got to balance your own equation. And get a marker that works. Well, blues. Equal masses of hydrogen gas and oxygen gas. Okay, hydrogen gas, and this is where you have to remember, these are diatomic molecules. Hydrogen gas is that. And oxygen gas is that. And that yields water. Now you have to balance it. Right? You can do the budget if you want, but this one's fairly simple. You need 2 oxygens on that side. Now you need 4 hydrogens on this side. So you're done. Now, equal masses of hydrogen gas and oxygen gas. So we've got X grams here, we've got X grams here. All right. So what's the ratio in mass? Well, that's 2.02 is 4.04 grams of hydrogen. We're doing the mass ratio like we did before. And this one is 32 grams of oxygen. Right? So if they're equal masses, right, then this one's excess and that one's limiting. Oxygen is limiting. A is the answer. We don't need more information. We got the answer. So in this case, right, start at the top, find the right answer, stop. Okay. And the race is pretty good too. 64. We did one like this at the end of the chapter discussion, at the end of the PowerPoints, where we work backwards. I think. Did we do that? That's too long ago, right? Okay, for this reaction, N2 plus H2H2, and I'm leaving out the phases again, yields N2H4 liquid. If the percent yield for this is 82%, 82% yield, what's the actual mass of hydrazine produced when 25.57 grams of nitrogen is reacted with 4.45 grams of hydrogen? Oh, this one's easier than one we did in class, during the lecture. Okay, what we have to do is decide which one of these is limiting, and then that one determines the theoretical mass of hydrazine. So how many moles is this? Well, let's see. We need grams on the bottom, moles on the top. So nitrogen would be 28.02. Because each one is 14.01. Right. Look it up. Okay, so this one equals 2557 and divided by 28.02 is 9126, 0.9126 nitrogen, grams of nitrogen. Let's go ahead and convert that to hydrazine. By the way, that's a dangerous, very dangerous chemical. The Germans used to use it in their little rocket plane. Remember that when you ever see pictures of it? It's a little one it's got sort of a gull wing and then one tail, right? And no stabilizers. It's what they call the hypergolic fuel. In other words, when you mix it with the oxidizer, it instantly reacts. You don't have to ignite it. And a lot of people die just fueling the things. Okay, let's see. This one has one here, one here. Oh, so we got that. So this one produces 0.9126 grams of hydrazine. Okay, how about this one? Now let's see. We need to convert that hydrogen 2.02 because there are two of them, right? 4.45 enter in 2.02 divide is 2.203, and that's hydrogen, grams of hydrogen. Not moles of hydrogen, excuse me, moles. How many moles of this would be? Be half of it, right? So that would be 1.10 or 115. No, that's not right. Let's see, just over 1 moles of hydrazine. Okay, so this is the least amount right here. The limiting reactant is nitrogen. So we convert that to mass. Oh, we already did, didn't we? No, this is moles. I'm sorry. This is moles. Nobody told me. Just let me get away with murder. Okay, we're going to convert this to mass now. So 2 nitrogens, 28.02, and 4 hydrogens, 4.04 is 3206. And times 0.9126 is 29.26 grams. And that's theoretical. Actual is 25.57. Oh, wait a minute. The reaction. Oh, percent yield is 82%. There it is. So this one has to be multiplied by 0.82. We use the fractional equivalent. Uh, 23.9915. But we've only got well, this is an exact number, percent. So we'll look to the others. This one has 4, so we can keep 4. 23.99 all rounded. Excuse me. That's wrong direction. 24 is the closest answer. 24.0. Is the actual yield of this reaction. see, we're still in chapter 3. What's the molar mass of tetraphosphorus decoxide? So you just need to know how to write that compound, correct? This one should be fairly easy. Tetraphosphorus decoxide, calculate the molar mass. Greatest number of moles of carbon atoms. I'm gonna let you do that. What you have to do is find out how many moles of compound do you have. Moles of compound, and then the ratio is how many carbon atoms per mole, how many carbon moles per mole of compound. Maybe I need to do it. At least get you started. So let's do the first one. Which of the following samples contain the greatest number of moles of carbon? So you set up Henry Ford, and the first one would be 58 grams of C4H10. So if we convert that, we need 4 carbons and 10 hydrogens, which is 2211. Okay. Cancels grams. And divide that into 58. So that's 2.62. 2.62 moles of compound. Then you have to multiply this and get rid of the compound and leave you with carbon. Should be carbon. Moles of carbon. And the ratio is, for every 1 compound, you have 4 carbons. Okay? So the compounds cancel. 4 times 2.62 is 10.5 moles of carbon. Right? And do that for each one. This ratio here will change depending on the formula. Right? That one's 2, this one's 1, and that one's 6. So my guess is it's going to be this one. Yeah, 180 grams of that compound.
Since we got kicked out of the building today for lack of water, I've come home and I'm going to finish the review for exam 2, beginning with chapter 3, number 70. So the way we're going to do it from here on in is I'm going to share the screen. And let's see, share, here we go. There it is. Okay, I think what I'll do is maybe expand my, let's see, will it let me? I have to change the view. Well, okay, that's all right. When I process the video, I'll split the screen between the board and the shared screen. Okay, we left off. we were just starting on number 70 of chapter 3 in the review document. So since I'm not time restricted now, and we're not pushing to finish the class before the lab started or any other restrictions, I'm going to take time and do these completely, the rest of them. So number 70 in chapter 3 says an unknown molecule is found to consist of 24.2% carbon by mass and 4% hydrogen by mass. And the remaining mass is due to chlorine. What's the molecular formula of the molecule given that the molar mass is found to be approximately 150? So it doesn't say exactly 150, it says approximately 150. Let's see if we can work with that. The information we have at this point tells me that we can easily determine the empirical formula. So let's do that first. 24.2% carbon. Carbon. We have 4% hydrogen. And the rest is chlorine. So let's see, I'm going to need my calculator. How do we know how much chlorine is? Well, 100% is the total. So if carbon and hydrogen make up this much, chlorine will be the rest. So we just add those two together and subtract them from the 100. Let's say 24.2 and 4. Yes, and then 4. So that's 28.2, and we subtract that from 100. 71.8. And this is by mass. So now we know what to do. Assume that you have 100 grams sample. That means 24.2 grams carbon, 4.0 grams hydrogen, and 71.8 grams chlorine. Now we've got something to work with. And we can convert each one of these. I'm going to have to write kind of small. We can convert each one of these by using the molar mass. And I never called your attention to this before, but notice that the molar mass is flipped, which is fine because it's a conversion factor. And all conversion factors are equal to 1, which means we can flip them as needed. And what we need is the grams on the bottom so we can cancel the grams here. Okay, so chlorine is 3545 grams per mole. Hydrogen is 1.01. And carbon is 12.01. All right, so now with my calculator, we can determine how many moles of carbon that is. 24.2, 12.01. So that's 2.015. That's moles of each one. So 4 divided by 1.0, well, 1.01, that's 3.96. And 71.8 divided by 35.45 is 2.025. So I think it should be fairly obvious now that at this point, what we're encountering here, is experimental error. And under these circumstances, it's okay to approximate. So this is very close to 2, this is very close to 4, and this is very close to 2. So we can say that empirically speaking, this is 2, this is 4, and this is 2. That means the empirical formula is C2H4Cl2. All right. Now, remember what we're looking for, since this is the empirical formula, we're looking for the multiplier. So in order to do that, we've got to find out what is the empirical weight. So we need 2 carbons, 12.01 times 2, 4.04 for the hydrogens, and 35.45 times 2, and that is 98.96. So this is 98.96 grams per mole of formula unit. And the problem says that the molar mass is approximately 150. So the molecular weight is approximately 150 grams per mole. All right, so here's the way we're going to approach this. If the multiplier is 1, then the value here is 98.96. 98.96. So that can't be it. This can't be 1. What if it's 2? Then it's 198. If X equals 2, then molecular weight equals 198. Well, that's too large. Right? I'm wondering, did I do this right? 24.2% carbon divided by 12 is about 2. That's right. 4 is about 4, yeah. And then left over, is this right? Let me check it out. 24.2, 4 plus 100. 71.8, that's right. Divide that by 35.45, that's about 2. Okay, so this is right. 242 is the empirical formula. Let me see if I added those up right. Okay. And hydrogen. And then 35.45 enter 2 times plus 96. That's right. Okay. So it's not exactly this one and it's not exactly that one. It's kind of in between. So if it's approximately 150, then either there's a mistake in the problem or we picked the best answer. Here's my mistake. This is not the simplest whole number ratio, right? Because we can divide everything through by 2. So it's actually divide by 2, divide by 2, divide by 2. This is 2 and this is 1. So what we have here is 1, 2, 1. And the empirical formula should be half of that. 49.48. So let's erase this. This is 50. So X, if this is the approximate molecular molar mass, this is the empirical mass, then the ratio of this one is about 3. That's what X would be. X is approximately 3. So that means this is 36363. C3H6Cl3. 363. There it is. Right there. Okay. That was 70. How about 71? Naturally occurring iron contains 5.82% of iron 54, 91.66% of iron 56, and 2.19% of iron 57, and 0.33% of iron 58. And this one actually gives the atomic masses for each of the individual isotopes. These are actual values, right? So instead of using the whole number values up here, right, we'll use the actual values. So in order to do a weighted average, now we have, let's see, the first one is 53.940. And it contributes 0.0582 fractional for the percent. That's its contribution to the total. The second one is 55.935. And its contribution is the fractional equivalent of 91.66%, which is 0.9166. And the third one is 56.935. And that's worth 2.19%, or the fractional equivalent. And then let's see, the last one is 57.933. And its contribution is 0.33%. So if the decimal starts there for percent, then we move 2 to the right, it's 0.0033. That's its contribution. So now all we have to do, that's the thinking part. Now all we do is crunch the numbers and add them together. 940.0582. This is 3.139. This one is 51.270. 56.935 times 0.0219. Its contribution is 1.247, rounded off. And the last one has a very minor contribution, 0.0033. This is 0.19191. So we just add those together. Plus. Let's see. What did I do wrong? 1.139, 51.270, 1.247, and 0.191. 55.8. Let's see. 55.85. Atomic mass units. That's the average atomic mass for iron. Let's see, this one's not marked. We're going to skip this one. It would be interesting. But we've done one like that already. Okay. This series of questions, number 73, requires you to interpret the drawing So what you see here is a representation of the molecule on the left. This is what the actual molecule would look like if you could get small enough and see it. But what we want out of that is the empirical formula. What's the simplest whole number ratio? So notice if you have 1, 2, 3, 4, 5, 6 carbons, this is A, 73A. If you have 6 carbons and 6 hydrogens, that's the molecular formula. The empirical formula is the simplest whole number ratio. This is 1 to 1. There it is. The second one is 2 carbons and 4 hydrogens. The simplest whole number ratio here is 1 to 2, right? If you divide both of them through by 2, you get 1 and 2. You don't put a 1 there, of course, but you put a 2 there. All right. Next, let's take some counting. We got carbon, hydrogen, and oxygen. And so how many carbons do we have? There's 1, 2, 3, 4, 5, 6 carbons. Hydrogens. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And oxygens. There's an oxygen. 1, 2, 3, 4, 5, 6. All right. The simplest whole number ratio says that we would divide through by 6. That would give you 1, 2, 1. That's the empirical formula for C. And this one has carbon, hydrogen, and oxygen also. So its molecular formula has 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 10. 10 hydrogens and 2 oxygens. Okay. So what's the greatest common divisor here? 2. 2 will go into this one and give you 1. 2 will go into hydrogen and give you 5. And 2 will go into carbon and give you 3. So the empirical formula for this one is C3H5O. All right, we could do that one, but we've already done that type of problem already. So now we're into chapter 4. All right. Chapter 4. Number 1. An unknown substance dissolves readily in water, but not in benzene. Benzene is a nonpolar solvent. Molecules of what type are present in the substance? Remember, like dissolves like. And what's the difference between water and benzene? This is nonpolar. This is polar. So anything that dissolves in water is going to be polar, or at least have a polar functional group on it somewhere. So it can't be this one. The solute molecules must be polar. They can't be both. Nonpolar doesn't work because the substance does not dissolve readily in, the unknown substance dissolves readily in water, but not in benzene. So it cannot be nonpolar. Polar is the best answer for this one. All right. Number 5. Which of the following is not a strong base? Remember, strong bases are hydroxyl compounds of metals from either the alkaline metals or the alkaline earths. So A is from an alkaline earth, right? Calcium hydroxide is, yes, that would be considered a strong base. KOH, yes, that's a strong base because it's formed from an alkali metal. Ammonia. Ammonia is a weak base. At this point in our studies, you have to take that one on faith. Right? We haven't gone into discussions of acid-base equilibrium yet, and that comes in the second semester. So you just have to take it on faith that ammonia is a weak base. And I'll show you in a second. Lithium hydroxide lithium is from the alkali metals, so it is also a strong base. Oh, strong base means it's not answer the question, doesn't answer the question, doesn't answer the question. We're looking for one that's not a strong base. And strontium is an alkaline earth, so it's also a strong base, which means it doesn't answer the question. So by process of elimination, the only one left is ammonia. And what you find with ammonia is that when you put it in aqueous solution, it reacts with water. Right? And it takes the hydrogen off of that water molecule and makes an ammonium ion plus a hydroxyl ion. And that's where the basic character comes from. But this particular reaction says that it much prefers to be over here, like this. It makes very little. It reacts with water only slightly. So it is a weak base. And in the second semester, we'll get into much more detail about acid-base equilibrium. Six, yes. Okay. Which of the following is paired incorrectly? Okay, so how about A? Is H2SO4 considered a strong acid? Yes, it is. So A is correct. HNO3. Is HNO3 nitric acid? Is that a weak acid or a strong acid? It's a strong acid. So this one is incorrect. And we could go through the rest of them to see if they're paired correctly, but test-taking technique says if you've got unique selections for each one of your multiple choice answers, you get to the first one you find that answers the question is where you stop. Right? We could look at barium hydroxide is a strong base, hydrochloric acid is a strong acid, and ammonia is a weak base. Right, so B is the one that's not paired correctly. All righty, number 7. The man who discovered the essential nature of acids through solution conductivity studies. This goes back to our discussion of Just a second. Did we talk about this? Acids and bases, how do we define them? Did we cover that in, I don't remember if we did. Pause. We did not. We did not cover this topic. It may be in your textbook. That's the only reason I could assume that it's a valid question if it's in that chapter in your textbook, chapter 4. But since we're here, Savant Arrhenius proposed a definition of acids and bases, and we haven't got to that yet. That's in the second semester where we get to that in detail. But so now you've been introduced to it. Arrhenius is the one who discovered the essential nature of acids through his solution conductivity studies. So we'll let it go at that. It's just definitional. All right. Number 9. 16.4 gram sample of hydrogen fluoride is dissolved in water to give 2 × 10⁻² milliliters of solution. What's the concentration in molarity? Remember the definition of molarity. Equals moles per unit volume, and that volume is in liters. So we have to convert hydrogen fluoride, which is a gas in its pure state, into moles of HF, and then ratio it with the final volume. So it's fairly simple calculation. Let's see, we need grams on the bottom, moles on the top. So what's the molar mass of hydrogen fluoride? Well, see, hydrogen is 1.01, and fluorine is, I believe it's rounded off 19. Yes, rounded off 19. So that's 20.01. We're going to divide that into 6.4 is 0.3198 moles. So the molarity now is 0.3198 moles in how many liters? 2 × 10 squared. 2 × 10 squared milliliters is how many liters? Well, we move the decimal place. First, we need to convert it to standard notation. So 2 × 100 is 200 milliliters, which means 0.200 liters. And that's 1.599. We're going to have to round it off. 1.6. Excuse me. 1.6. I did something wrong. 0.3198. This is 200 milliliters, which is 0.2 liters. Let me do that again. 0.3198.2 divide. Yeah, that's right. It's rounded off to 1.6 molar. $16.4 grams. Oh, see what I did? I covered up my 1 with a parentheses. All right, so let's try that again. 16.4 now divided by 20.01 is 0.8196. 0.8196 divided by 0.2. That's 4.10 molar. There it is. That's the best answer. 4.1 is D. Okay, let's try this one. Let's keep my board centered. Here we go. 14. What's the mass of calcium chloride? What mass of calcium chloride is needed to prepare 3.950 liters of 1.49 molar solution? So back to our definition, right? We need to know the mass, but we don't have access to mass here. We can get moles and then we can convert to mass. So if we solve for moles, that's molarity times volume, which is 1.49 molar times volume in liters is 3.950. And that's equal to 5.886 moles. Now we need to convert moles to grams. So we need to use calcium chloride's formula to determine its molar mass. Let's see. I want to get something closer so I don't have to stretch my mind. Well, I guess I'm going to have to. Calcium and chlorine. I know chlorine, but calcium is 40.08. 40.08 for calcium, and then 2 times 35.45 for chlorine, which is 110.98. So this is 110.98 times that value, which is 65 point, let's see, we have 3 significant figures, 65.3 grams. Okay, I made a mistake somewhere. Oh, misread my calculator. 653 grams. There we go. 653 grams dissolved to make 1.49 molar solution dissolved in 3.950 liters of final solution gives you a 1.49 molar solution. 16. What mass of solute is contained in 256 milliliters of 0.838 molar ammonium chloride solution? Okay, so we can use our formula to determine the moles of ammonium chloride. Then we have to convert it to mass. Yeah, I'll go ahead and do it. So in order to find the moles, we rearrange the equation so it's molarity times volume gives you the moles. Right? So that's equal to molarity is 0.838 molar. Then the volume has to be in liters. So 256 milliliters, move the decimal to the left 3 places for thousand place is 0.256 liters. So that'll give us the moles of ammonium chloride. .2145 moles. Okay, now we have to convert to mass. Right? So how do you get the mass of ammonium chloride? You have to be able to write the compound. You need to know the formula. Ammonium is a polyatomic ion with a 1+ charge. And the chloride is a -1 charge. So that's it. You just need that formula. So nitrogen is 14.01. 4 hydrogens are 4.04. Add that together. And chlorine is 35.45. So we have 5350. 53.50 times 0.2. And that's 11 point, let's see, 3 significant figures. 11.5 grams of ammonium chloride. All right. How about 17? Let's see what we got going with 17. I'm going to move that further. I'm going to move that up out of the way. I feel kind of squished in here. 17. We'll put 17 up here. There we go. All right. 74.28 gram sample of barium hydroxide is dissolved in enough water to make 2.45 liters of solution. How many milliliters of this solution must be diluted with water in order to make 1 liter of 0.1 molar barium hydroxide? All right. This problem is a 2-step problem. First, you have to find out what is the concentration of the stock solution, we call it. The stock solution has this much barium hydroxide dissolved to make this much solution. Then we do a dilution problem with that molarity. Okay, so the first thing we have to do is, what is the molarity of the stock solution? Well, we're going to need the molar mass of barium hydroxide to convert 74.28 grams into moles. So barium hydroxide. Barium is a big atom. It's 137.33. And notice that the hydroxyl is inside of parentheses with a 2 subscript. So we have 2 oxygens. 16 times 2 is 32. Add that in. And 2 hydrogens, which is 2.02. So we have 171.35. 171.35. And we divide that into 74.28. And that gives us 0.4335 moles of barium hydroxide. Okay. Now we calculate the concentration. That many moles of barium hydroxide per liter. How many liters? 2.450 liters. So that gives us a concentration of 0.1769 molar. Okay, so this would be equal to molar 1. Right? We want to know what volume of that to dissolve in 1 liter. So molar 1 is this value. Molar 2 is given as 0.100. Okay. Volume 2 is 1 liter. That's the final volume. And volume 1 is our unknown. It's important that you set these things up correctly so that when you use the formula, the numbers go in the right place. Otherwise, you'll get the wrong answer. So we're going to use the formula M1V1 equals M2V2. So we have M1, 0.1769 times volume 1, which is our unknown. And then molarity 2 is 0.100 times 1 liter. Okay, so this side is still 0.1. See, how many zeros do I have? 2 zeros. Okay, and this side, and then now we have this one unknown times that. So if we take this one out of the numerator here and put it in the denominator here, then that's equal to the unknown volume. So we'll take that and divide it into 0.1 and 0.565 liters, 0.565 liters. Our answer is in milliliters. So 1 liter is 1,000 milliliters. That means this is 565 milliliters. Notice the unit of measure got small, went smaller. That means the number has to get bigger just to keep you honest and going in the right direction. So the answer to that one is A, 565 milliliters. All right. 18 is another dilution problem. I don't know that we even need to do that one. What I'll do is I'll pull the data together and show you how to set it up, and then you finish it off. let's see, that's 18. 18. All right. So we're starting off with the way you know this one is a dilution problem is you've got a beginning concentration of sulfuric acid, you have an ending concentration, you have an ending volume, but you don't have a beginning volume. So that tells me, and if we set it up like we did in the lecture, we'll say concentrated, volume concentrated, molarity diluted, volume diluted. So what's the concentrated molarity? It's 18 molar sulfuric acid. Okay. What we want to know is how much of that is it going to take to make this arrangement down here. So this one is unknown. We don't know how much volume we're going to pull out of that concentrated sulfuric acid container. So we want to prepare 2.30 liters, 2.30 liters, and we want the concentration to be 0.145 molar. Okay, so there you have it, the values assigned to their variables. Now you need to plug them into the formula, MC VC equals MD BD, and solve for this one. And you should get 19 milliliters. The answer is going to come out in liters. Then you convert it to milliliters. The other option you can do is convert this to milliliters. Right? So we'll move it 1, 2, 3. 2, 3, 0, 0 milliliters, and put milliliters in here, right here. Put that in there, remember? And because this is in milliliters, that answer will be in milliliters. And it should be 19. All right, let's try different types of reactions. This one's not highlighted, but I think we'll go with it anyway. How to classify your reactions. (26). Okay. So we have these these reactions, lead 2 plus ion plus 2 iodine ions yields lead iodide. 2 cerium 4 plus and 2 iodines yields iodine plus 2 cerium 3 plus. HOAC. That's an abbreviation for this compound. Right? This is acetic acid. So what we've done is this is acetate. And this hydrogen makes it acidic. Okay, so that's what it means. All right, these are examples of what types of reactions. Well, this first reaction, looks like a precipitation, and I'll explain. If we take this lead ion and this iodide ion and make this compound, if you look it up in the document, the document with the shaded squares and the clear squares, I don't have a copy handy with me right now, but if you cross the lead 2 plus with the iodine ion, you'll find that lead iodide is insoluble. So that first one is a precipitation. That's a precipitation reaction. The second one, notice that cerium changes its charge. Its oxidation state goes from 4 plus down to 3, or up to 3 plus. And the iodine goes from -1 to a 0 oxidation state. That is a redox reaction. Okay. This one is an acid, and that's a base. This is an acid-base reaction. Okay, which one fits that? E satisfies that description. Each one respectively, precipitation, redox, acid-base reactions. Okay. Let's do 28. Okay, 28. Let's see, we have zinc bromide, aqueous, and silver nitrate. This looks like we're setting ourselves up for a double replacement reaction. All right, so what happens? Well, the silver trades places with the zinc. So silver and bromine get together. There's the silver and bromine. And the zinc and the nitrate get together, only it's still in solution. Right? So what type of reaction is this? It's a precipitation reaction, right? Because you get this solid. So the first one is precipitation. The second one, we've got KBr, aqueous, and silver nitrate. Silver reacts with, we made a solid in both of them. And they're both double replacement. These are both precipitation reactions, right? Both of them, times 2. That's why the answer is C. They're both precipitation reactions. '29. Here we go. All of the following reactions can be classified as. Oh. Okay. 29. So the first one, notice, remember the rule of thumb I gave you. If you've got a reaction where there's an element on one side and it shows up in a compound on the other side, it can go either direction. You could go compound to element or element to compound. When that happens, that is a redox reaction, oxidation reduction reaction. Same thing for the second one. There's oxygen in the compound, and it's a free element on the right-hand side, on the product side. That's an oxidation reduction. This one, we could look at it similarly. Oxygen here is a free element, and here it's in a compound, and here it's in a compound. But it's also a combustion reaction. Methane, it's not letting me highlight. Methane plus oxygen burns. It's a combustion reaction, and all combustion reactions are redox. So all 3 of these reactions are oxidation reduction. Okay. All right, so let's skip 30 and see 32. Which of the following salts is insoluble in water? Let's see, 32. So what we need here is our solubility chart. And you look at sodium and sulfide together, and you find that they're soluble. You look at potassium and carbonate, and you find that they're soluble. You look at lead 2 plus and nitrate, and they're soluble. Then you look at calcium and chloride, and they're soluble. All of these are soluble. Now, if we had memorized the solubility rules, we know that all alkali metals are soluble. So sodium, potassium are all soluble. All nitrates are soluble. And most chlorides are soluble. Right? This is one of the chlorides that is soluble. All right, so if you memorize the solubility rules, you don't have to look at the chart. But that's okay. You'll have the chart available for the exam. All right. We get 2 on the screen at one time. So this is 37. Consider an aqueous solution of calcium nitrate added to an aqueous solution of sodium phosphate. What is the formula of the solid formed in the reaction? So you've got to be able to write the formula for the compound in order to proceed with this, to answer this question. So we've got calcium nitrate. Calcium and nitrate is a polyatomic ion. It's got a 1 plus charge. This one has a 2 plus charge. 1 minus charge. Right. So this one we need 2. There's your formula for calcium nitrate, and it's soluble. And it reacts with sodium phosphate. There's another polyatomic ion. This is a 3 minus and this is a 1 plus, so we need 3 of those. Okay? So when they react, what happens? This is a double replacement reaction. Remember, in solution, these are all soluble. You have calcium ions, sodium ions, nitrate ions, and phosphate ions all mixed together. So they have the opportunity for sodium to interact with nitrate. Okay? And that is soluble. And then you have calcium interacting with phosphate. This is a 3 minus. This is a 2 plus. So this one will be 2, and this one will be 3. Notice I cross multiplied. 3 comes over here, 2 goes over there. So the formula for our, and look it up in your solubility chart, and you find this is a solid. This is our precipitate. Calcium Ca3, PO4 taken twice. Ca3, PO4 taken twice. That is the solid that's formed in this reaction. Oh, that one's already up. 38. The balanced, let's see. Oh, 38 depends upon this statement right here. Aqueous solutions of barium chloride and silver nitrate are mixed to form solid silver chloride and aqueous barium nitrate. So they were kind enough to tell us what the products were, but they didn't give us the compound formulas. So we have to do them ourselves. Barium chloride. So where's barium? Barium is an alkaline earth. It has a +2 charge. Halogens have a -1, so we need 2 of those. Okay. That's aqueous. I'm not going to write that up there. Silver nitrate. Silver is a 1 plus charge. Nitrate is a 1 minus charge. That's it. So it forms silver chloride. That is a solid. And barium nitrate. Barium nitrate. And we need 2 of these because that's a 2 plus. This is a 1 minus. Okay. Now, notice that in the answer, you've got coefficients. So what we're looking for is the balanced equation and the coefficients if they apply. All right. So maybe I better write this in here. This is aqueous, and this is aqueous. Okay, let's balance them. Right, one silver on either side. Two nitrates. Right, so I better put two nitrates over here. Two nitrates. So now I have two silvers, and two chlorides, one barium. That's balanced. Right, you can check it for yourself and see that it's balanced. The balanced molecular equation contains which one of the following? The molecular equation is exactly the way we wrote it here. So silver chloride solid? No, because it has a 2 coefficient. So this one would be proper. And we look at the others. Barium nitrate, it has a 2. No, that's not it. Barium nitrate, no, it has a coefficient, a subscript for nitrates, and this one's not right either. Okay, so B is the only one that comes out of that equation. 39 breaks that equation up into a complete ionic equation containing which of the following terms? Okay, so now these are individual ions. Barium, 2 plus, 2 chlorides. We have 2 silver, and these are all aqueous, and 2 nitrate. And on the product side, we still have 2 silver chloride solids. We can't break those apart. And then we have a barium, 2 plus, and we have 2 nitrates. There we go. And these are both aqueous. And these are all aqueous also. So do we have a 2Ba2 plus in here somewhere? No, it's just Ba2 plus, not 2. Do we have a chloride? Yes, but it has a prefix, it has a coefficient of 2, right? So that's not right. 2 silver ions, yes. On the reactant side, we do have 2 silver ions. So we found our answer. If we look at the nitrates, they need a 2 coefficient, and silver chloride is not aqueous, it's solid. Okay, so C has to be the answer for this one. Now we go to the net equation. So how do you find the net equation? You look on both sides, reactants and products, and if you have the same species on both sides, they cancel. Right? Barium, barium. Barium, barium cancels. Chloride. Nope, got to keep it. Silver. Got to keep it. Nitrate. Okay, so we have 2 chlorides, 2 silvers, and 2 silver chloride solids. But remember, we have to, when we write an equation, it has to be the simplest whole number ratio, right? So each one of these has a 2 in front of it. That means that the net equation is 1 chloride plus 1 silver ion yields 2, yields 1 silver chloride solid. And these are both aqueous. So now we can look for the answer. Ag plus, yes, that's there. Barium's not there. Nitrates is not there. Hydrogen's not there. Silver chloride is a solid. So again, A is the only one that fits out of that group. All right, so let's clear the board. And what number is this? 45. See, is my board squared again? There. 45. When solutions of strontium chloride and sodium sulfate react, which of the following is a spectator ion? All right, strontium chloride. Strontium chloride. Now, where's strontium? Strontium is an alkaline earth. It has a 2+ charge. So that means we need 2 chlorides. 2 times the -1 balances a 2+. Right? So this is aqueous solution, and we're reacting it with sodium sulfate. This is a 2-, that's a 1+, so we need 2 there. All right. Which of the following is a spectator ion? Well, the easiest way to determine this is to say which ions form the solid. And if you look them up, sodium chloride is soluble, right? So the sodium and the chloride are spectators because the strontium and the sulfate form an insoluble compound. Excuse me. Right? So the spectator ions are the chlorides and the sodium. So there's the chloride, there's the sodium, excuse me. And that's why the answer is 2 of these. There's lots of repetition in there. All right, here's an acid-base reaction. This is 50. All right. What mass of sodium hydroxide is required to react exactly with 25 milliliters of 2.7 molar H2SO4? All right. When they react, what is the equation? H2SO4 reacts with sodium hydroxide to yield sodium sulfate plus water. Remember, OHs and hydrogens make water. Okay, now we have to balance the equation to find out what is the stoichiometric ratio between sodium hydroxide and sulfuric acid. So we need 2 sodiums here. Okay, that gives us 2 hydroxyls and 2 hydrogens. So if we have 2 hydroxyls, like that, and 2 hydrogens, like this, right? There's one water, there's the other water. So we need 2 waters. And that should be balanced. Right? 2 hydrogens, 4 hydrogens, 4 hydrogens. 2 oxygens, 2 oxygens. That doesn't count these oxygens. 1 sulfate, and 2 sodiums. That is a balanced equation. Now we can do the stoichiometry. 25 milliliters of 2.7 molar. There we go. If we multiply these together, we're not going to get molar, we're going to get millimolar. So you can either change that to liters to find out how many moles of sulfuric acid are available, or you can go ahead and multiply these 2 together and get millimoles. (67.5) millimoles is how many moles? Well, remember the milli is 10 to the -3. So that's equal to 67.5 times 10 to the minus 3 moles, or 6.75 times 10 to the minus 2 moles. And this is sulfuric acid. Okay, I'm going to make some room here. Now we need to convert this into moles of sodium hydroxide so that we can calculate the mass required. So 6.75 times 10 to the minus 2 moles of sulfuric acid will be converted to sodium hydroxide with the ratio of 2 to 1. Right? So 2 times that value, there we go, is 1.35 times 10 to the minus 1 moles of sodium hydroxide. Okay, so now we just need to convert that into mass. And I'm going to have to make some room here. So let me do away with this and this. See, make sure it's still straight. Okay, so this is 0.135 moles of sodium hydroxide. So we need our conversion factor is moles on the bottom, grams on the top. There we go. So what is the molar mass of sodium hydroxide? Let's see, we need sodium is 23. Oxygen is 16. Hydrogen is 1.01. So that's 40.01 times 0.135 is 5.40 grams of sodium hydroxide. Best answer is this one right here. Excuse me. 5.4 grams. I'm not sure. Oh, I see why it was rounded off to 2 because of this 2.7 molar. Right. So that should be rounded off to 2 significant figures. All right, let's see. Oxidation states. All right. '52. In which of the following does nitrogen have an oxidation state of +4? So we might as well set these up by Henry Ford and just slog through them. So there's A, B, C, D, and E. All right. So this one is HNO3, NO2, and N2O. And NH4Cl and NaNO2. Okay. All right. So remember the rules. Hydrogen in this position is a +1. Oxygen is a -2. So we have a -6 and a +1 equals a -5. So that means this nitrogen has to be a +5. Okay, that's not it. NO2. So with -2 for the oxygen, we have a -4 that has to be balanced by a +4. Yes, that's our answer, right? And we don't have any 2 of the above, none of the above, anything like that. So we found our answer. You can do all the rest of them if you want, but if you're in a hurry in an exam, that's where you stop. All right, 53. 53 simply asks, what's the oxidation state of iodine in iO3 minus? Okay. There's -2 for each one of these oxygens, which means a -6 total. But remember, the sum of all the oxidation states has to equal the charge on the polyatomic ion. So this has to reserve out one of these to hold that minus. That means we only have to balance a -5. So that's a +5. And a +5 and a -6 is a -1. So our answer is +5. All right, 55. Which of the following statements is not true? All right. A, B, C, D, and E. When a metal reacts with a nonmetal, an ionic compound is formed. That's true, essentially true, yes. B, a metal-nonmetal reaction can always be assumed to be an oxidation-reduction reaction. Yes, if you start with the elemental metal and the elemental nonmetal, and they react, you always get an oxidation-reduction reaction. Electrons are transferred. C, two nonmetals can undergo an oxidation-reduction reaction. Is that possible? Yeah. How about this one? Methane and oxygen. Right? Non-metal, non-metal. All nonmetals. We know that combustion reactions are redox reactions. So yeah, C is also true. How about D? When two nonmetals react, the compound formed is ionic. Nope. That never happens. And E, a metal-nonmetal reaction involves electron transfer. Yeah, that's true. Okay, so we found our answer, D. Uh, 56. In this reaction where calcium and oxygen yields calcium oxide, which species is oxidized? So we have two calciums plus one oxygen yields two calcium oxides, solids. Yes. Which species is oxidized? Okay. First, we have to determine what's the oxidation states of all the species. So these are pure elements. They're zeros by definition. This one's a -2. That means calcium has to be a +2. Okay. So what does oxidation mean? Oil rig. Oxidation is loss. Which one lost electrons? Well, the one that went from 0 to a positive. Right here. This is oxidized. So calcium was the species that was oxidized. There you go. And oxygen obviously had to be reduced. All righty. 57, that's a different equation, so let me get rid of this one. And 57. All right, in the reaction, 2 cesium plus chlorine gas yields 2 cesium chloride. Cl2 is Which one of those? All right. So 2 cesiums plus 1 chlorine gas yields 2 cesium chloride. Yep, that's right. Okay, so Cl2 is what? Well, let's see. These are zeros, zeros. This is +1, this is -1. So the cesium went from here to here. It was oxidized. That means the chlorine gas was reduced. Okay. The anything that's oxidized is also the reducing agent. And anything that's reduced is the oxidizing agent. Right? So let's see. They're asking about chlorine gas. Chlorine gas is reduced and it's the oxidizing agent. So there we go. Oxidizing agent. There's no reduced in there. It's not the reducing agent. It wasn't oxidized. Electron donor. No, it accepted an electron to go from there to there. Okay, so the only one that answers that is B. 61. Let's see. 61. All right. Which of the following statements is true? Oxidation and reduction can occur independently of each other. No. A is false. They always occur together. B, accompany all chemical changes. No. Not necessarily. Describe the oxidation reduction describes the loss and gain of electrons respectively. So oxidation is loss, true. Reduction is gain, true. So C is true. D. Oh, I misread A. Cannot occur independently. That's true. I misread. I read can occur independently. No, they cannot. They cannot occur independently. So A is true, B is false, C is true, and D, result in a change in oxidation states of the species involved. Yes, always. So D is also true. That means A, C, D, E. E is true. There's your answer. All right. We ought to be getting close. 63. Balance the following oxidation reduction reaction using the oxidation number method. In the balanced equation, the coefficient of Br minus is what? Okay. Using the oxidation reduction method. All right. So if we're starting off with this one plus this one yields this one plus this one, correct? Yeah. So the oxidation reduction method says you determine the state of each one, 0, 0, 3 plus, and 1 minus. Then we say here, this one lost 3 electrons for each iron. This one, the bromine, gained 1 electron for each bromine. Okay. Now, this method requires that the electrons transferred must balance. So this one transferred 1, this one transferred 3. So we need 3 electrons transferred from this one, but we've got 2 here, right? How do you get 3 out of 2? Well, here's what we can do. We can say, suppose now there are a number of ways to solve this, right? I'm inclined to say we need 3 down here, right, to give you equals 3 electrons, right? But now that balances the electrons, but now we have an unbalanced bromine. So how do you get 3 out of this one? Well, we can use the fractional, right? We can do that. And then, now that we've got 1 iron, 1 iron, we got 3 bromines, and we have the same number of electrons transferred in this ratio of elements, reactants and products. Now we can get rid of that fraction. So if we get rid of the fraction, we multiply everything by 2. So we have 2 Fe plus 3 Br2 yields 2 Fe 3 plus 6 Br minus. And that's balanced. So the coefficient for Br minus is 6. That's one way to do it. The other way would be to no, that's the best way. Now that I think of it, that is the best, that's the foolproof way to get there, using that fractional trick. Yeah, that's the best way. '66. Select the spectator ions for the following reaction. And it looks like there are no coefficients embedded in here, so we just need to identify the species. All right. Do we have spectators here? Well, let's see. Lead 2 nitrate is soluble. Remember, all nitrates are soluble. This chloride is also soluble because it's combined with an alkali metal, and alkali metals are soluble. So they're both soluble, we know that. All right, how about the other side? Lead 2 chloride, is that soluble? And you look it up in your chart, no, it's not. This is our solid right here. Okay, so that means the lead on this side and the chloride on this side need to be retained. And the nitrate and the potassium are spectators. So K plus and nitrate, those are the spectators. Okay, 68. Identify the precipitate formed, if any, in the following reaction in aqueous solution. So if we're going to swap partners, this ammonia would combine with this nitrate, right? Ammonium nitrate is soluble. All nitrates are soluble. And then iron and the carbonate combine. Okay, so we know that the iron and the carbonate are combining, but what is the charge on the iron? It's a 2 plus. Notice NO3 minus 1 minus taken 2 times mean that the iron has to be 2 plus. And the carbonate is 2 minus. So FeCO3 is the correct formula. FeCO3, right there. That's your precipitate. '69. In which of the following does nitrogen have the highest oxidation state? All right. So we should have kept going with that previous one, then we'd have that information already. All right. The highest oxidation state. So do you just go in and do your calculations for each one of those, right? And I think we found that this one, HNO3, is actually a +5. And that NO2 was a +4. And we do the calculation for N2O, that would be a +1, because oxygen is 2 minus, and nitrogen has to balance that with a 2 plus, but there are 2 of them. So each one is a +1. And D, the easiest way to do D is to recognize that that is our nitrogen species, that polyatomic ion. So this is 4 pluses. We have to hold 1 out. So 3 pluses, that means 3 minus. So 3 minus for that one. And then E is NO2. NO2 minus. This is -4 for the oxygens. 2 times -2. We hold 1 out for this charge. That means that this has to be +3. So yes, that has the highest oxidation state of those groups. Which one of these has iodine of the lowest oxidation state? 71. All right, lithium iodate. Okay, B, iodine dioxide. Iodine monoxide. Diiodine monoxide. Ammonium iodide, and E. Elemental iodine. This one's easy. That was 0. Okay. This one is a +1. This one is a -2. So that's a -6. And a +1 is -5. So this has to be a +5. Right. That's not a very low oxidation number. This one is a -2 times 2, which is a -4, which means +4 for this one. This one is a -2, so this together has to be a +2, but each one of these is a +1 because there are 2 of them, and both of them together have to balance that one. So this one is +1, and this one is a -1 because this one is a plus. Right? So the lowest oxidation number is this one right here. D, -1 for that iodine. All right. Okay. We could balance these. It might be instructive to do this one. That one looks kind of hairy though. Let's see, what's this one? This one might be troubled also. So let's go back to this one and try it. The reason I want to do this one is, notice this compound. That is the molecular formula for nitroglycerin. And these are the products when nitroglycerin goes kablooey. All right. So let's do that one for fun. $77. All right. Let's see if I can get enough room out of this thing. Let's see. I'm going to have to spread it. Nitroglycerin. C3H5NO3. C3H5. Yep. NO3 taken 3 times. And we're going to have nitrogen, carbon dioxide, water. Yep. Water. And oxygen. Okay. So let's set up our budget. Notice that this is a polyatomic ion, but it breaks apart over here. So we've got to treat all the elements separately. We've got carbon, we've got hydrogen, nitrogen, and oxygen. So on this side, we have 3 carbons, we have 5 hydrogens, we have 3 nitrogens, and we have 9 oxygens. On this side, we have 1 carbon, we have 2 hydrogens, we have 2 nitrogens, and we have 2, 3, 4, 5 oxygens. Okay. First off, notice that we've got an element here and an element there. So we'll hold those both till last and decide which one to go to first later on. For the moment, we've got 3 carbons here. So let's put 3 there. That makes 3 here. And that changes the oxygens to, let's see, 6, 7, 8, 9. Okay. How about hydrogens? Okay. There are 2 hydrogens here. There are 5 hydrogens here. Let's hold that one and see. Well, no, we got to deal with it, right? Because we got to hold these till last. So how do you get 5 and 2 out of these? Well, we could multiply this by 2 and multiply that by 5. If we did that, 2 here and 5 there, that makes 10 hydrogens, right? 10 hydrogens, but it also changes the carbons. So now we have 6 carbons, we got 10 hydrogens, we have 2 times 3 is 6 nitrogens, and 2 times 9 is 18 oxygens. On this side, we have 6 carbons. We have the hydrogens that we've planned on. The nitrogens, we still have 2. And the oxygens, we have 6, 11, 8, 9. Still have, well, that can't be. We have 5, 6, 7. 7 and 6 is 13, excuse me. 13 oxygens. Okay. All right. Let me see. These 6, 10 oxygens. We've got 18 oxygens over here. We need 18 over here. So how are we going to get 18 oxygens out of that? Well, let me think. Let's do Well, we still have to get nitrogens, right? We still have to get 6 nitrogens. So let's put 3 here. And then we've got oxygen at the end. We could work with this one, but oh no, wait a minute. We don't have 6 carbons over here. We only have 3. That's my mistake. We still only have 3 there. We have 6, 11, 12, 13. Okay, that's right. Oh, okay. Now let's balance the carbons, right? So we need to make this one 6. 6. Okay. Now what does that do to the oxygens? That's 12, 17, 18, 19. Right? 19. This is 9 times 2 is 18. That's right. This is 12 oxygens plus 5 is 17, 18, 19. Okay. So how did we end up with that? All right. We're going to use the fraction again. We only need half of that oxygen, right? If we take half of this oxygen, that cuts this down to 18, right? So look at it. There's 1, 5 is 6, 6 and 12 is 18, right? So we have 6, 10, 6, and 18. The equation is balanced, except we got that fraction. So now we got to get rid of the fraction. So we multiply the whole thing through by 2. Now that makes 4. Excuse me. 6, 12, 10, and 1, or nothing. There we go. So now our equation is balanced. 4, 6, 12, 10, and 1. There it is. Let's take a look at this one. You know what? This is going to be a neat exercise in combining the redox method with the budget method. So I think it would be useful to do this one. 78, this will be our last one, I'm pretty sure. All right. So let's set this up. KiHNO3. Let's see. KiHNO3 yields. KNO3, NO, I2, and H2O. Okay. Notice that this is a redox reaction. Here we have a 0, and here we have a -1. So we know it's a redox reaction. What we have to do is say, how are the electrons distributed? How are they transferred? This is a +1. This is a +1. We got a nitrate here, but it splits over there. So we're going to have to say, what is this one? This is -2, and that makes -6. This is a +5. Okay. This one is also a +5, and a -2, and a +1. This one is a -2, and this is a +2. And this one is a -2 and a +1. Okay. So now we can say the iodine loses an electron. It is oxidized. So this iodine, loss of 1 electron per iodine. And this nitrogen doesn't go here, it goes there. And this is a gain of 1 electron. Oh, excuse me. 3 electrons, right? From +5 to +2 is 3 electrons gained per nitrogen. Okay, so now we need to balance the number of electrons that move. What we need here is 3 electrons moving, but we've got a 2 there, right? So if we put a 2 here, that's only 2 electrons. So what we need to do is cross multiply. What we need is, instead of 2 electrons here, we need 6 electrons and 6 electrons here. Right? So if we want 6 electrons, we've got to multiply by 6, which means 6 here and 3 here. That gives us 6 iodines there, 6 iodines there. So that's 6 electrons. This one needs 6 electrons, so we multiply by 2, a 2 here, 2 nitrogens, and a 2 here, 2 nitrogens. Now, the transfer of electrons is balanced. Now we can move to our budget method, starting with this equation, not the original equation. All right, so I'm going to erase that. And this. And let's clean it up a little more. All right, let's get rid of these things. Now that we're not redox, we're not interested in redox anymore. Let's clean these up, just to keep it from being too messy. Okay, so now we do our budget. We've got a potassium, we've got iodine, we've got hydrogen, we've got nitrogen, and we've got oxygen. Potassium, iodine, hydrogen, nitrogen, oxygen. Okay, how many potassiums on this side? 6. Iodines, 6. Hydrogens, 2. Nitrogens, 2. And 6 oxygens. On this side, we have 1 potassium. We have 6 iodines. Yep. We have hydrogens, 2 hydrogens. Right? And nitrogens, we have 1, 2, and how many oxygens? We have 3, 4, 5, 6. The only one that's not balanced is the potassium. Okay. We can work with that. So if we're going to balance the potassiums, we need a 6 here. All right, 6 there. that changes the number of nitrogens on this side, right? So we have 6, 7, 8 nitrogens. Okay. We have 3 times 6 is 18, 19, 20, 21 oxygens. Okay. All right. So now we've thrown everything out of kilter again. We've got an element over here, so we're going to save the iodines till last, just in case we mess them up. Let's see. What do we got? 6, 6, 2. Okay, nitrogens. We need 8 nitrogens on this side. So we have to change this one from 2 to 8. So that gives us 8 nitrogens. That gives us 8 hydrogens. That gives us 24 oxygens. Okay. Now we've got an imbalance of hydrogens, right? So where do we get hydrogens? Over here. We need 8 hydrogens on this side. So a 4 there will give us 8. That'll also change the number of oxygens. So now we have 3 times 6 is 18, 19, 20, 24. 24 oxygens. 24, 8, 8, 6, 6. We are balanced. Okay. That's the way it's done. Combination of redox method and budget method. And that should be it. Yes. So you see useful information here, right? All of that useful information, including the polyatomic ions and the periodic table, and the this is the solubility chart. All of those things will be available on the exam.